Hello everyone and welcome to Jigyasa Analytics webinar on using AI to generate synthetic customer data. My name is Krishna Mehta and I will be joined today by my colleagues Pat Bhattacharya, Shikha Agarwal and Ratna Sinha. Today we will talk in details about the process we put in place to generate the synthetic customer data, and then we will have a shorter session tomorrow where we will talk about the business applications of synthetic customer data. Let us start by asking the question, what is synthetic data? It is artificially generated information that mimics real world data. It is derived using mathematical algorithms, statistical processes, and artificial intelligence. Now, in recent years, the use of data in making business decisions has exploded. We see that in fundraising, we see data being used in marketing applications, customer acquisition, customer retention. We see it in credit risk, in fraud detection, in collections, and many, many more applications. Now, with that have come data security concerns as data breaches are very common. And there has been this push about data privacy for customer data, and there are regulations being put in place for what can the data be used for and how it can be accessed. So, because of all that, it is almost always true for synthetic data applications that it does not contain any direct or inferable private information. Now, synthetic data generation process have been around for some time. They were simulation exercises done earlier where certain distributional assumptions were made, and based on that, uh, certain real world realizations were conjured up, and what the impact would be was calculated. Now, taking that further, in the early 2000s, there was the SMOTE process, which was very promising. But the real advances have been made in the last few years due to the advent of artificial intelligence, particularly in the areas of large language model and computer vision models. And my colleagues will talk more about that, but this has significantly improved the quality and the feasibility of generating synthetic data. We will talk about why we need synthetic data and the business applications associated with it in greater details in our follow-up webinar. But let me give you an overview here. So there are the data privacy regulations like GDPR and CCPA, which have come up to protect consumer rights. And using synthetic data clearly helps with that. We talked a little while ago about how the use of data has exploded across organizations and it being used to support various business functions. But with that comes the inherent security threats. Clearly, if some of these could be done using synthetic data, those security threats are reduced. But the use of synthetic data is not limited to privacy and security. There are many, many very interesting and useful business applications of synthetic data. Uh, Very often, I talk to colleagues or clients about a new product they have launched, a new market they have gotten into, and they do not have enough data to build a model or make any um, data driven inference on how they are doing, how they can mitigate their risks, anything related to that, and they have to just conjecture. Then there are very rare events like fraud, where there isn't a critical mass for a long time to build something using data science. And then there might be underrepresented groups within the customer base, but the business wants to do something with them, but there isn't enough data. In all these situations, if we could use synthetic data to augment real data, we could get to using data science and making better business decisions, sometimes faster, sometimes for the first time, leading to cost savings, greater revenues, greater efficiency for the organization. And then another application we must be aware of is that as we propagate the use of mathematical algorithms, all these algorithms are selecting customers or excluding applicants based on a formula. And in doing that, there are some inherent biases being built into your customer base because certain groups are being underrepresented or eliminated altogether. And over time, this can lead to the customer base becoming very different than the general population. And in the future, when you try to analyze the customer base to try to get to a new market or build a new model or new application, you will be dealing with biased data, which will give you incorrect results. And using synthetic data, you can mitigate some of these biases. As I said, we will talk about this in greater details in our follow-up webinar. Now, I will hand over the presentation to my colleague Pat, who will take us through the amazing models that have come up and been developed to generate synthetic data.
Hello, everyone, and thank you for attending this presentation. My name is Pat Bhattacharya, and I will take you through some of the synthetic data generation methods. The field of synthetic data generation is not new. It is commonplace in many industries to either use rule-based methods or some kind of statistical distribution-based methods to create synthetic data. For a few years now, deep learning vision models have been used to generate new images. More recently, we have seen examples such as ChatGPT, where deep learning language models are being used to generate new textual content. The success of generative AI in creating realistic new images and useful text has led to a great deal of recent research in harnessing the power of deep learning methods to create synthetic tabular data. These methods train neural network models to build synthetic datasets. Since vision and language models worked so well in generating new images and content, researchers have recently tried to apply some of these same methods to tabular datasets, and those are shown on this slide. Variational autoencoders compress an input dataset to a lower dimensional space, which captures the most important features of the high dimensional input dataset. Another sample from the same lower dimensional space can then be decompressed to create new synthetic samples. Generative adversarial networks consist of two neural networks working against each other. One is a generator that generates fake or synthetic data, and the other is a discriminator which is trained to discriminate between real and synthetic data. The generator and the discriminator work against each other until the generator produces high-quality synthetic datasets that the discriminator cannot distinguish from real datasets. Diffusion models progressively add noise to training data until all features are completely random. The model then learns to reverse the process and create new synthetic samples from noise. Lastly, tabular data can be converted to a textual format and then fed into a large language model, which can then spit out new synthetic textual data that is converted back to tabular format. For our experiments, we focus on methods based on diffusion models and large language models, as those are more recent and have been shown to perform better than the earlier methods based on GANs and variational autoencoders. The three specific methods we experimented with were GREAT, which is based on large language models, Tab DDPM, which uses a diffusion model to create synthetic samples, and Real Tab Former, which also uses a large language model. However, this method is faster than GREAT, and this method can also be used to create relational databases and seemed interesting to us. I will now hand it over to Shikha, and she will explain each of these methods in detail.
Thank you, Pat, for handing it over to me. Now let me walk you through about the architectural detail of the three synthetic data generation methods that we have used in our experiment. The first method is GREAT, which stands for Generation of Realistic Tabular Data. GREAT uses a large language model and we have used Distill GPT-2 in our experiment. Although GRADE supports any transformer-based autoregressive model, the key requirements are compatibility with autoregressive decoding and input text format. Just like GPT-2 is used in NLP, GRADE follows an autoregressive process, which means it predicts each token in a sequence one after another based on the preceding tokens. Another powerful feature of GRADE is conditioning. We can pre-specify values for specific columns. This allows GRADE to generate realistic yet controlled synthetic data by predicting the next token conditioned on the pre-specified values. Let's walk through how GRADE actually works by breaking the whole procedure into two main stages, training and sampling. The training phase starts with the shuffling of the columns. This prevents the model from memorizing the column position and encourages it to learn the relationship between the variables more flexibly. Then converts the records to sentence. Each row of the tabular data is transformed into a natural language sentence. For example, age is 39, gender is female, income is 50K. This makes the input data more LLM friendly. These sentences are then used to fine tune a LLM model. We are using the Distill GPT-2 model, so it learns to generate data sequence based on the observed patterns. The result is a model that has learned the distribution of the dataset in an autoregressive way, resulting in predicting one field at a time based on the prior field. Let's come to the sampling phase. In the sampling phase, when generating synthetic data, we begin by setting up a prompt. This is useful for scenario testing and control experimentation. This can be done in two ways, feature only and conditional prompting. In feature only, just specify the column names like age and gender, and in conditional prompting, provide the fixed values like age is 39, gender is female to guide the generation. Then feed this prompt to the fine-tuned LLM model. The LLM model will convert this prompt into token, and LLM generates an output string. Then a pattern recognition module parses the output back into the structural tabular format. In the end, we will obtain a synthetic tabular data that mimics the real data while preserving the privacy and enabling robust analysis or model development. Now let me introduce Real Tab Former, Realistic Relational and Tabular Transformer. This model is designed especially for working with relational and tabular data domains where traditional language model often fails. The key point is that Real Tab Former uses large language model GPT-2 The GPT-2 is a powerful autoregressive transformer model, means it looks at the previously generated token in a row to predict the next token. The next and perhaps most innovative feature is that real-time former supports relational databases with parent-child relationship. This means it's just not limited to flat tables. It can model data where one table references another table. Now let's take a closer look how real-time former handles relational data. Let's start with left side labeled as non-relational parent. Parent table is our starting point. We input it into the GPT-2 model, which is then fine-tuned on the parent table data. This fine-tuned model generates synthetic parent data. Now let's move to the right-hand side, labeled as child. From the synthetic parent record, select one synthetic parent record and use it to query the child table. We collect the true child record that correspond to the synthetic parent, and we'll use the fine-tuned GPT-2 model from the left side as frozen encoder to encode the synthetic parent record, and true child records are fed to the sequence-to-sequence decoder along with the synthetic parent record, which then generates the synthetic child records. Let's now turn to TAB-DTPM. TAB-DTPM stands for Tabular Denoising Diffusion Probabilistic Models. It uses diffusion models which are popular in image generation but are now being applied effectively to structure tabular data. The core idea has two processes, a forward diffusion process and a reverse process. In forward diffusion process, we gradually add noise to the real data over many steps. Think of it like progressively blurring a clear image. In the reverse process, a neural network is trained to reverse the noise step by step to generate new realistic data samples. One of the strengths of TAB-DTPM is that it often performs exceptionally well on both numerical and categorical data, especially high cardinality categorical fields, which are often a challenge for other generative models. Now let's discuss the working principle of TAB-DTPM. We start with the raw tabular dataset, which contains both numerical and categorical features. Before feeding the data into our model, we pre-process it. Numerical features are normalized and categorical features are one-hot encoded. Next, we separate features based on their type. Numerical features are modeled using Gaussian diffusion. Categorical features are modeled using multinomial diffusion. These separations allow the model to handle different data types effectively, preserving their distinct statistical characteristics. At the heart of the TAB-DTPM is a neural network trained using denoising objective. Noise is added to the data, simulating a diffusion process. The model learns to reverse this noise effectively, generating realistic synthetic data. This is optimized using backpropagation and loss function, enabling the neural network to approximate the reverse diffusion process accurately. Once trained, we move to the generation phase. We start with pure noise. This noise is gradually denoised through the reverse diffusion process. The result is high quality synthetic data that mimics the original dataset in distribution and structure. Now let me talk about dataset used in our experiment. We have used two different datasets. The first one is related to credit risk. This dataset is publicly available and based on Australian credit card data. It contains 14 masked attributes and approximately 700 records. This dataset is suitable for testing how well different methods perform with financial tabular data with limited size. The next dataset is from the domain of consumer marketing. It includes lapsed subscriber data with 70 attributes selected for this exercise. This dataset is much larger, containing around 20,000 records. One important point to highlight is that all the experiments were done entirely on Jigyasa's GPU-enabled server, ensuring no exposure to the cloud and maintaining strict data privacy. Next, I will hand it over to Pat and she will discuss evaluation of synthetic datasets.
We perform three types of experiments to evaluate the quality of our synthetic datasets. In our first experiment, we tried to see whether a machine learning model can distinguish between our real and synthetic datasets. Our hypothesis is that if these models cannot distinguish between real and synthetic datasets, then the synthetic dataset that we generated must be quite similar to the actual dataset. In the second set of experiments, we tried to evaluate how well the synthetic data preserves the privacy of the original dataset. Is it possible to get some of the actual data back by reverse engineering the synthetic data? Lastly, we also try to evaluate the utility of synthetic datasets, and the question we ask in this test is how a model built on synthetic data performs when applied to the actual data. Depending on the business applications, one of these tests might be more important than the other.
In this slide, I will talk about the evaluation result of synthetic data versus actual dataset check on credit risk dataset. In this check, we have trained a classifier to distinguish whether a record is from the real dataset or from the synthetic dataset. The idea here is simple. If the classifier performs very good, it means the synthetic data is easily distinguishable from the real data, which is not ideal. If the classifier struggles, means AUC is closer to zero point 0.5, it means the synthetic data is very similar to the real data, which is what we want. To set a reference point, we have created a baseline model using only real dataset. We randomly split the real dataset into two parts. One part was labeled as real and the other part was labeled as synthetic. We repeated this process 20 times, training a classifier on each split to see if it could distinguish between the two. Because both splits are actually real data, the model is just guessing with no meaningful pattern. As a result, the average test AUC in case of baseline check is 0.49, which is near random performance, and this is expected. When trained on data generated using GREAT, the model achieves a very high training data AUC of 0.77, validation data AUC of 0.77, and test AUC of 0.78. In contrast, for real transformer and tabbed DTPM, AUC scores are around 0.56 and 0.58, much closer to the baseline. From the result, we can summarize that model is able to distinguish between great synthetic data and the real data. However, the real transformer and tabbed DTPM datasets are closer to the real data, and the model is unable to pick up the difference between them. Now I will show you the synthetic versus actual check on marketing dataset. For baseline, train, validation and test dataset AUCs are 0.580, 0.501 and 0.498 respectively. For GREAT method, AUCs are 0.812, 0.801, 0.815. In case of real transformer, we have training AUC of 0.641, validation AUC of 0.631 and test AUC of 0.633. In case of tab DTPM, training AUC and validation AUC are 0.891 and test AUC is 0.892. The interpretation from the above results are: model is able to distinguish between all the synthetic dataset and the real dataset. This distinction is more pronounced for GREAT and TAP DDPM.
This page compiles the information from the previous two slides, and we can compare the synthetic versus actual checks between our two datasets. We can see that the AUC numbers in the lower table is higher on average than the AUC numbers in the table above. This means that the distinction between the synthetic and actual datasets are more pronounced for the marketing dataset than for our Australian credit risk dataset. Our marketing dataset is larger and contains many more features than the Australian credit card dataset. This may be one reason why the synthetic samples we create using the marketing dataset are less similar to the real datasets. One thing worth mentioning here is that even though there seem to be differences between these synthetic and actual datasets, this does not seem to affect their utility, and models built using these synthetic datasets still perform very well in holdout samples, as we will see later in this presentation. A very important reason for creating a synthetic dataset is that real datasets contain private information and there are ethical and legal restrictions to sharing this information. When creating synthetic datasets, it is therefore very important to make sure that the privacy of the real data is preserved and synthetic datasets are not too close to the actual datasets. One of the privacy metrics we use is match count or identical match share, as it is often called. This checks for very close matches between the synthetic records and actual records. We define a synthetic record as a close match if it lies within a 3% confidence interval of a record in the actual dataset. Usually, we prefer the match count to be less than 9% so that fewer than 9% of the records in the synthetic dataset are close matches to the records in the actual dataset. The table on this slide shows the match count numbers for the synthetic samples that we created. The row headers on this table identify the synthetic sample, and the column headers identify the original dataset. So the second column in this table shows the match count numbers for the 3 synthetic samples created using the credit risk dataset. And the third column shows the numbers for the 3 synthetic samples that we created for the marketing dataset. Note that lower match count numbers are better. Thus, we can see from the numbers that the tab DDPM synthetic samples shown on the last row of this table perform very well on this test for both the credit risk and the marketing datasets. The great synthetic sample, which is shown on the first row of this table, also performs well. The middle row shows the results for real tab former, and real tab former does fine on the credit data but has a weaker performance on the marketing sample as the match rate is higher than 9%. Another metric that we look at to evaluate the privacy of synthetic datasets is the distance to closest record, which measures the distance between each synthetic record and its closest neighbor in the actual dataset. These DCR values are calculated for each synthetic record, and the median of these values is usually reported. Higher values of median DCR are better, as it implies a lower chance of breach of privacy. For each record in the actual sample, we can also calculate the distance to its closest neighbor in the actual sample. We can also therefore obtain a median DCR for the actual sample and use it as a benchmark to compare the median DCR for the synthetic sample. Therefore, we calculate the median DCR ratio, which is equal to the median DCR for the synthetic sample divided by the median DCR within the actual sample. Higher values of this ratio are better, and ideally we would like this ratio to be greater than 1. This table shows the median DCR ratios for the credit risk dataset. We can see that for great and real tab former synthetic samples, median DCR ratios are less than 1. And for the tab DDPM synthetic sample, the median DCR ratio is greater than 1. This table shows the results for the marketing dataset, and we see similar results here as well. These median DCR ratios allow us to rank the synthetic samples, and this is shown on this third table. Tab DDPM, of course, shows the best results in this test and would get a rank of 1. Real tab former would get a rank of 2, and great would get a rank of 3 based on their performance in this test. So overall, TAB DDPM synthetic dataset performs very well again on this privacy check. Great and real tab former seem closer to real records. Perhaps the best way to evaluate a synthetic dataset is to build a model using the synthetic data and see how well that model performs on real data. In order to create a benchmark for this test, we decided to split our real sample into three parts: modeling, validation, and test samples. The table here shows the AUCs in the three samples when we built this model on the real sample. For the Australian credit card data, the AUC in the modeling sample is 0.78, the AUC in the validation sample is 0.77, and the AUC in the test sample is 0.75. For the marketing data, the AUCs are slightly higher and approximately 0.79 in all three datasets. Next, we combine the actual modeling and actual validation samples to create a new training sample, and it was this sample that was used to build the synthetic dataset. The original test sample from the actual dataset was used as a holdout sample to evaluate the performance of synthetic datasets. In order to build a model with the synthetic data, we again split the synthetic dataset into modeling, validation, and test samples. Next, I will hand it over to Ratna, and she will take us through some of the results we got when building models on synthetic samples.
Thanks, Pat. Hello, everyone. I am Ratna, and I will take you through the results of credit risk and marketing model. The models that were built using synthetic dataset and how they performed on holdout sample is shown on this slide. This slide shows the result for Australian credit risk data. The first row once again shows the baseline model built on actual data. Notice that since test sample is kept aside as holdout sample, the AUC for test sample and holdout sample are same for the first row. As we can see, it's 0.751 for both. The second row shows the AUC from the model built on great synthetic sample. After building a model, we had scored the model on holdout sample that we had kept aside, and we got the AUC of 0.754. The third row in the table shows the AUC from the model built on real tab former synthetic sample. When this model was scored on holdout sample, we got the AUC of 0.754. The last row of the table shows the AUC from the model built using tab DDPM synthetic sample. When this model was scored on holdout sample, we got the AUC of 0.746. Overall, all the models had performed well on holdout sample, but synthetic dataset that were built using LLM model seems to perform little better than the synthetic model built using diffusion models. This slide shows the result for marketing dataset, and directionally we see similar results here as well. Once again, the first row shows the baseline model built using actual marketing dataset. The second, third, and fourth row shows the result for the model built using GREAT, real tab former, and tab DDPM synthetic sample respectively. When scored on holdout sample, the GREAT synthetic model has an AUC of 0.784. The real tab former synthetic model has an AUC of 0.810, while tab DDPM has an AUC of 0.761 for the holdout sample, which is comparatively low compared to other two synthetic models. Now Pat will take you through the overall results.
We combine all the results on this slide to understand the differences in performance between the three synthetic samples. We show match count, median DCR rank, and performance on the holdout samples all together on this slide. As we have seen before, lower match count is better, and we can see that overall tab DDPM performs the best in terms of match count. Tab DDPM also performs the best in terms of median DCR rank. So overall, when it comes to privacy measures, Tab DDPM, which is the synthetic dataset created using diffusion methods, performs the best. It has the best rank in terms of median DCR and also the lowest match count. However, its AUC in the holdout sample is slightly lower than the other two methods. So we have a trade-off between privacy and utility. Models that perform better in terms of privacy also may perform slightly lower in terms of AUCs, whereas models that show high AUCs may have some breach of private information. For us data scientists, perhaps the most important measure of utility is how does a model built on the synthetic data set perform when applied to the actual data. We found that large language models perform slightly better than diffusion models in our holdout samples, although all three approaches did very well in our holdout samples, generating AUCs greater than 0.74 in each case. So in this final and most important test, all our synthetic samples performed really well. And since many of the samples also preserve the privacy of the true dataset, these deep learning based approaches to create synthetic datasets seem to be very useful and can have many business applications when data is scarce or cannot be accessed due to privacy reasons. Next, I will hand it over to Krishna, and he will take you through some of the interpretations of the results and also talk about what comes next.
Thank you, Pat, for those most interesting results. So as we saw that the diffusion models and the LLM models all have a role to play. The diffusion models do really well on privacy measures, but they do fairly well on model performance as well. The LLM models might have specific use cases, specifically if we are looking for sampling in a particular way, or if we are looking into relational databases. So, in all of this, the question is how do we take our work on synthetic data forward? So, what we would like to do is start working on customized industry and business specific applications, as that will allow us to zero in on the kind of model to use in a particular scenario to add value to the business process. Now, we have been also continuing our ongoing research on artificial intelligence. In particular, we have been doing a lot of work on computer vision models, which combine image and textual data. And we will be organizing a webinar on it soon. We think that this area has a lot of possibilities, especially because it will allow us to mine a new kind of data which is generally not available for predictive models. And in all of this, we are looking for partners who would be interested in working together with us and join these experiments. I would like to thank you all for taking the time to join us today for this presentation. I would also like to acknowledge my colleague Barkha Agarwal, who did significant work on this project. Now, let us move on to question and answers.